Okay, welcome back to Aromaticity, Chapter 15, Lecture 2. This is Part 3. Let's look at methodologies used for the reduction step in the Friedel-Crafts acylation reduction reaction that we just saw previously. These are two examples of more general methods available to reduce a ketone carbonyl group to a methylene group. The Clemmensen reduction uses an acidic solution of zinc dissolved in mercury as the reducing agent, and the Wolff-Kishner reduction uses hydrazine under basic conditions. So we're going to reduce this carbonyl group to a methylene group, as you can see highlighted in yellow. So let's go to the next slide. As you can see on this slide, we're going to prepare alkyl benzenes with straight chain alkyl groups by coupling methods. So also the coupling reactions we saw earlier can be used to prepare alkyl benzenes with straight chain alkyl groups. So we're going to revisit the coupling reactions. These were covered in Chapter 10, reactions of alcohols, amines, ethers, epoxides, and sulfur-containing compounds. And we're going to see these on the subsequent slides in this series of slides from Chapter 15. We're going to look at the Gilman reaction and other reactions related to that one as we go through here. As you can see, Gilman, Still, Suzuki. So one of the alkyl groups of a Gilman reagent can replace the halogen of an aryl halogen. In the Still reaction, it couples an aryl halide with a steinane compound. The Suzuki reaction couples an aryl halide with an organoborane, which is obtained from the reaction of an alkene with catechol-borane. This is the Gilman reaction. Bromobenzene reacts with diethyl lithium cuprate to yield ethylbenzene and ethyl copper. What has actually happened is one of the alkyl groups of the Gilman reagent has replaced the halogen of an aryl halide. So we start with bromobenzene, diethyl lithium cuprate, and we form ethylbenzene and ethyl copper, but we actually transfer one of those, replacing the halogen of the aryl halide. Now let's look at the next coupling reaction. This is the Still reaction. Bromobenzene reacts with tetrapropylsteinane to yield propylbenzene in this particular example. And moving right along, this is the Suzuki reaction. Chlorobenzene reacts with an organoborane to give propylbenzene. The synthesis of organoborane is shown on the next slide, this molecule right here. So let's take a look at that. This is the synthesis of organoborane. An alkene reacts with a catechol-borane to make an organoborane. There are many different alkenes will do this. So you can see the variety of types of organoboranes we can make that will set us up for unique reactions to follow. So with a variety of alkenes being available, almost nearly any type of alkyl benzene can be easily prepared, ultimately. It is important to have more than one way to carry out a reaction, as we'll see as we progress through the various reactions of organic chemistry, for various reasons. Another functional group in the molecule could react with the reagents we're using to carry out a desired reaction, so an alternate method might be very useful to get around this additional reaction of another functional group. The next slide shows an example of what we're talking about. Let's say we desire to reduce a carbonyl group into a methylene group. Of course, up here we have the Clemmensen reduction. Strong acid reagent is present. Then down here we have the Wolff-Kishner reduction, and OH group remains unchanged, as you can see right here. There's a strong base reagent present. This shows the Clemmensen reduction versus the Wolff-Kishner reduction. The conditions of the Clemmensen reduction, as you can see up here, zinc and mercury and hydrochloric acid, would result in substitution of the alcohol group with a chlorine. Under the basic conditions of the Wolff-Kishner reduction, as you can see here, the alcohol group is unchanged. Meanwhile, we have accomplished what we set out to do with the carbonyl group on the other ring. Notice, both cases they've been reduced. But in this case, we've also undergone another change in the molecule. If a compound has a group that requires both strong acids and strong bases be avoided, an alkyl substituent could be added to the ring by using one of the coupling reactions instead of alkylation reduction. So we can use coupling reactions to avoid both the Clemmensen and the Wolff-Kishner reduction reactions. Okay, now let's look and talk about another group of compounds known as arene oxides. When an aromatic hydrocarbon, such as benzene, enters the body, it is enzymatically converted into arene oxide. This is a compound in which one of the double bonds of the aromatic ring has been converted into an epoxide. This is the first step in changing an aromatic compound into a more polar, water-soluble compound that can eventually be eliminated. Cytochrome P450 enzymes detoxifies aromatic hydrocarbons by converting them into arene oxides. So we can take the benzene ring with cytochrome P450 in the presence of oxygen. We can create benzene oxide, an arene oxide. And then, through what's shown on this slide, we can, due to the oxygen in the molecule, we can make it more polar and more water-soluble and more excretable. So this slide shows the two ways an arene oxide can react. It can react as a typical epoxide, undergoing attack by a nucleophile to form an addition product. Or it may rearrange to form a phenol, as you can see here. Something epoxides such as ethylene oxide cannot do. The mechanism for the arene oxide rearrangement is on the next slide. So let's take a look. Here it is. As you can see, benzene oxide on the left will undergo a rate determining step as it undergoes rearrangement. So let's look at this mechanism for arene oxide rearrangement. This shows the formation of phenol, which is the result of arene oxide rearrangement. This is an example of an arene oxide undergoing rearrangement. The three-membered epoxide ring opens, picking up a proton from the solution. Instead of losing a hydrogen right away to form phenol, the carbocation forms an enone. There's the enone. As a result of the 1,2 hydride shift, which has occurred right here, forming the enone. It is called an NIH shift. Of course, the work was done at the National Institutes of Health because it was first observed in the lab at the National Institutes of Health from the work that was being done. The first step is rate determining, so the rate of formation of phenol depends on the stability of the carbocation. The more stable the carbocation, the easier it is to open the epoxide ring and form phenol, as you can see here. So we got a 1,2 hydride shift, sometimes known as the NIH shift, occurring and forming the enol, and then it forms the phenol. All right, here's an example of an arene oxide rearrangement. Only one arene oxide can be formed from naphthalene because the double bond shared by the two rings cannot be epoxized of the naphthalene structure, two benzene rings together, and in the middle there's a double bond between the two. Since benzene ring is so stable, the molecule is more likely to be epoxidized at a position that leaves one of the benzene rings intact. So naphthalene oxide forms as shown in this slide. Naphthalene oxide can rearrange to form one naphthol, up here, 90%, or two naphthol, 10%. The carbocation leading to one naphthol is more stable because its positive charge can be stabilized by electron delocalization without destroying the aromaticity of the benzene ring. However, the positive charge on the carbocation leading to two naphthol can be stabilized by electron delocalization only if the aromaticity of the benzene ring is destroyed. Therefore, rearrangement leads mostly to one naphthol. This is favored over this one, which is less favored, as you can see illustrated in the slide. And it's spelled out more, this is more stable, can be stabilized by electron delocalization without destroying the aromaticity of the benzene ring. There it is. Here, we're going to destroy the aromaticity of the benzene ring by this movement of the electrons away from the benzene ring. Okay, let's look at why some aromatic hydrocarbons are carcinogenic. Some aromatic hydrocarbons, such as benzene, are carcinogenic because they are converted to arene oxides. If we had a benzene ring up here, and in the presence of cytochrome P450 and oxygen, we would form the arene oxide. As is illustrated on this slide, 2-deoxyguanosine, a component, it's right here, a component of DNA, has a nucleophilic amine group that is known to react with certain arene oxides. When a molecule of 2-deoxyguanosine becomes covalently attached to an arene oxide, the 2-deoxyguanosine can no longer fit into the DNA double helix, and as a result, the genetic code will not be properly transcribed, which can lead to mutations, which eventually can lead to cancer. So that is a very clear example of the dangers of the formation of arene oxides, or the epoxide structure itself. Okay, that concludes Aromaticity, Chapter 15, Lecture 2.